Hello everyone, welcome to this trial class by Smart Solver Academy. So, uh, although we have a few audience, we hope that the session will still go well, and we would love it if you make it interactive, ask your queries, and try to stop us where we are not clear. So let's progress. Second, yeah, good. So this is a combined trial class for both our programs, How to Solve It and the Math Olympiad program. And we will go into the details of each of these separate programs in the next few slides. But before that, I just wanted to say who we are. So we are a team of 3 passionate educators, and we want to really spread the joy of mathematics amongst the Indian students, which unfortunately I think the school curriculum or the usual entrance exams don't convey enough. Here's a quote by my favorite mathematician, John von Neumann, where he says that mathematics is a primal neurological language, and we really hope that by taking our curriculum, you are able to feel this for yourself. But enough about us. If you want to know more, you can always visit our website, which will also be available to you in your emails after this talk. Okay, great. So before we start with the actual trial class, I wanted to say a few more words about our philosophy and our pedagogy. So there are many math classes around, and we want to tell you what distinguishes us from them. So in this program, what we really intend to do, in both the programs, what we intend to do is invigorate your logical faculties. We want you to learn the lessons for yourselves, and we want to facilitate that. We don't want to spoon feed you. We don't want to just provide you the solutions. So what will be more emphasized in this curriculum is how you arrive at the solution rather than just knowing the solution. Because if you know that thought process, if you can get trained in that, it will be very easy for you to become a good problem solver, and you'll be able to apply it to many aspects, even outside of mathematics. And that is our philosophy. Now, how will we come good on this philosophy? It will be with our instruction and the methodology we follow for that. So we want to formulate and reinforce a meta strategy for problem solving. And you will see through various examples that we take later in the course of this presentation and during the actual courses that we will emphasize that you follow a meta strategy to solve the problems and not give in to ad hoc approaches, because they don't usually lead you in. Just a second, I'll check. There are some chat messages.
I think we are doing chats.
Okay. All right, good. So that's the first point. Yes, the PPT gets stuck. Yeah. So one thing which you will realize is that we will try to present each solution of all the puzzles, the games, the questions you see in our courses as a consistent and logical story, which will be, I think, very unique. I haven't seen this as many places. And there is a famous article by Tim Gowers. Many of you might not know who he is, but he's a Fields medalist, he's a legendary mathematician, where he says that it is important to present a solution as perspicuous, which means that the solution should be presented such that you don't feel like a magical step has happened anywhere. So some of you might be experienced with Olympiad mathematics or have some familiarity with it. And you might know that oftentimes it feels like a rabbit was pulled out of the hat. What we want to do is actually we unveil the magic trick to you so that you do not see it like a rabbit coming out of the hat, but it will still be wonderful. And another thing which we'll emphasize is that once you know the solution, either by yourself or by looking at the solution, you learn from it and not just move on. And we will show this by actually doing it for a few examples, where we will analyze and generalize each solution. We'll try to learn meta and specific principles from it. And we term this process as solutionization. And we'll, of course, cover a wide variety of techniques through the courses. Okay, great.
Here so, Siddharth, 1 second. I would just like to encourage the participants to turn on their videos so that it is easier for the speaker and for even the moderators, so that it is more interactive. If for some reason you can't do it, then you can't do it. But I just wanted to prompt you guys.
Yeah. If you can do it, that will be great. So here are some meta principles that we will be following. And we'll actually be demonstrating these meta principles to you, some of them at least, in the course of today's presentation. And I think this is what we are really going to convey, that by following the meta principles, you can arrive at many solutions which were earlier out of your reach. These problems tend to be very difficult. And if you are not acquainted with them, you will be pretty much lost. At least I was when I started my journey. And these are things which some books do go into. But oftentimes I've realized that online or most books actually don't dwell a lot on these topics, which are, I think, more important than any individual solution. So here's a very simple meta principle, right? If you are stuck somewhere while problem solving, it's not only maths, any other problem solving aspect of your life. If you're stuck somewhere, you should go and question the last decision you made, which brought you to the current state where you're stuck. Oftentimes, just going back and thinking about, oh, what were the alternatives at that step helps a lot. In fact, so much so that it becomes implicit in a mathematician's way of thinking, but oftentimes they don't say it out explicitly, and students are sort of left to pick it up on their own. But we wanted to make this explicit. Another thing which is very, very common in a lot of Olympiad problems and a lot of puzzles that come up is that there will be a particular parameter, which you will see very shortly. And by just varying that parameter, you will realize that things become very easy if you just take the problem to its extreme ends, either by making the parameter very small or very large. Thinking about the penultimate step often helps, which just means that, oh, you want to get a particular solution, and you're just asking yourself, what could be the second last step? What could be the step which would lead me to the solution? Often thinking about this in reverse helps you arrive at the actual solution. And this, for me, is the punchline. This is George Polya's advice, that if you cannot solve a problem, you find an easier problem you can't solve. Like all of what I just said in so many slides and wasted so much of your time could be summarized in this one point, right? And this you should really take to heart from today's presentation. I don't think I need to even demonstrate how to use this advice, because it's so simple and so well written that when you are stuck at a problem, you just try to find an easier problem that you can't solve. And if you keep doing this, if you keep progressing, eventually you'll solve the problem you started. Okay, great. So enough about our pedagogy and philosophy. Now for some actual details about our program. So we have two programs, as I said, How to Solve It and the Olympiad program. So the How to Solve It program would last for about 8 to 10 sessions. Each session would be about 1.5 to 2 hours. The aim of the program is that you develop a meta thinking mindset. We will teach you about how to think and get to the solution rather than, just tell you what the solutions are. It will involve loads of games and puzzles, and it will have a flavor of Olympiad maths. The games and puzzles would be general. They could easily arise in a day-to-day conversation, for instance, but they would also have an element of Olympiad mathematics in them. And of course, during our lectures, we will do a lot of problem solving, and there'll be engaging home assignments, which would not feel like burden. I hope they would actually be so interesting that you might have trouble completing other homework because they won't. Yeah, sorry, Abhishek seems to have.
Yeah, so there is a question on the chat by Ishan. How do we know which is the easier problem since we cannot solve it either? So what is easy in quotes?
Okay, so the easiness of the problem is something which is subjective. Of course, what is easy for one might not be easy for somebody else. But as you become acquainted with the problem statement, you realize where the difficulty is. And once you realize where the difficulty is, you start to sort of take away from the problem while maintaining some essence of that difficulty. Of course, these are all more words. The best way to convey what this advice is to show you actually how it works in action. Let's see if we can get to this advice at some point today. We in fact will. You will see in the last puzzle that we take today how this advice is at play. Okay. So the easiness here just refers to taking away from the problem something or making some additional assumptions which don't take away at the spirit of the problem. Like the difficulty that you feel the problem has still survives, but you just get extra gadgets because of the assumptions that you made, or because there might be some parameter which you gave an actual value to. That would transfer to this advice here in this situation. Okay, good. I think there's another chat question. Oh, yeah, good. So let's move on. Okay. And now to the Math Olympiad program. So the Math Olympiad program will be the continuation of the How to Solve It program. Once you are acquainted with those techniques, we will start training you in a rigorous manner for the Indian Olympiad cycle. So the first step of the cycle is the IOQM, which is something which we did not have when we were growing up. We only had the RMO, but I think since many people are writing the RMO now, the IOQM has been introduced. So we will first take a prep course, which would train you for these exams all the way up to the Regional Maths Olympiad. And depending on how well students perform and what the situation is, then we will extend this course to actually also cover material from the Indian National Maths Olympiad to the International Maths Olympiad level, which is, of course, like if you can make it there, that would be quite incredible. And the duration of this would again be 8 to 10 sessions per month, with each session being roughly 1.5 to 2 hours. Okay. And here I wanted to emphasize an important point. Like many of you in the form wrote that you have some Olympiad experience. Some of you wrote about INMO, or I think one of you wrote about a pre-qualifying exam in Nepal or something like that. But a couple of you wrote about the IMO, that you have appeared or you are about to appear for the IMOs. So I wanted to emphasize that unfortunately, many Olympiads are floating in the Indian circuit with the same name, or names which are very close within it, like a few letters of each other. When you go outside India and you tell someone about the International Mathematics Olympiad, it means only one thing, which is the International Mathematics Olympiad represented by this logo, right? And I can tell you this from personal experience, and almost anyone will agree that the level of this Olympiad is way, way beyond the other Olympiads floating in the Indian circuit. And it's actually way beyond probably the toughest exam that you have in your mind, which is JEE. Like it is, winning an Olympiad at the IMO is probably, I think, one step below just getting your name into the history books of maths. It is pretty difficult and intense. So there is a question here. Good. All right. So this is about the Math Olympiad program. And if I haven't already motivated you enough or scared you enough, why should you do these courses? So the first thing is that one thing which we really hope will happen is that you will be able to experience the joy of maths through these programs. Forget about what fame or what other skills they might develop. You will be able to enjoy mathematics for once in your life. And it will obviously also boost your cognition. The other thing which will be, I guess, the biggest selling point of the course will be that it will help you to win medals in Olympiads, or at least progress further in the Olympiad cycle, in the Indian Olympiad circuit. And if you are able to do that successfully, it will be sort of a red carpet for you to enter into the big colleges, not just in India. In India, I know that CMI or the likes, like institutes similar to CMI, do have a special entry for Olympiad winners. But even colleges outside recognize Olympiads very heavily. And the same goes for financial and technical interviews. So if you are at some point going to apply for a job in a finance firm or a tech firm and you have an Olympiad medal in your CV, that counts for a lot. And more than that, during the course of your preparation, you will realize that it becomes very easy for you to ace these interviews, these different puzzle questions that are generally asked. So I think this was my interview experience, a small anecdote that I was in IIT Kharagpur doing mechanical We were all lost back then. Nobody knew what was mechanical, but we all did some engineering. And at the end of 4 years, when we sat for a job, the questions asked to us by companies which were the most prominent ones, like taking a job in mechanical engineering itself wasn't the first choice for almost anyone. And when you go to these other companies, all they used to ask, like at least I went to Citi's interview, Citibank's, and all they asked me are these kind of brain teasers and Olympiad like puzzles. So that unfortunately is not taught to you in the curriculum because these things are orthogonal. If you have some background, it will put you at a huge advantage. That's all I want to say. So, okay, finally some action. We've sort of chit-chatted a lot and nothing interesting has happened till now, but now something interesting is about to happen. So good. Is everyone ready for their first puzzle? So here it is. If some of you have seen it before, I'm sorry, I apologize, but please don't spoil the fun for others. So here is your task. As you can see in the picture, there are 3 boxes named A, B, and C at the bottom of this rectangular shaped cutout. I don't know. It's not exactly a rectangle, but I don't know what to call this shape. So fine. And you have 3 boxes at the top, which you can see the names are sort of rearranged. The ABCs have been rearranged. And your task is to use wires and connect these 3 boxes with each other. Of course, connecting A with A, B with B, and C with C. And there are some rules. So what are the rules? I'll describe the rules visually. So here are the rules. The first rule is that your wires cannot cross each other. So I hope all of you can see what I'm scribbling on the screen. So something like this, for instance, is not allowed because here there is a crossing, right? Your wires cannot cross each other. So this is not allowed. Wires cannot touch the outside boundary. So you cannot also do this. So like something like this is prohibited. You cannot cross the boundary. And you also cannot pass through a box. So your wire cannot go like this and, cross through A. This is not allowed. You have to stay. You can only touch the box outside. You cannot go through it. So respecting these constraints, you have to accomplish your task. And this is precisely the question. Is it possible to complete these tasks under the given set of rules? If something is not, please ask. We will be more than happy to clarify. Yes, Abhishek.
Yeah, so I just wanted to mention you can't move any box. It's not like you can lift the boxes down below.
Good.
You can't.
Yeah. Thank you. Thanks for letting. So the boxes are stationary, like you cannot move them. They are welded to the ground. All you have to do is use wires and connect these boxes with each other while respecting these constraints. And we'll give you a minute or a minute and a half to think about it and try to think logically, or at least also, like at the end of this exercise, more important than the solution will be analyzing how you thought about the problem and whether that can be improved. In the meanwhile, we will create a poll, which you will see appear on your screen, and you can basically tell your opinion in that poll about this problem. But take your time thinking about it. We will resume discussing this problem in a minute or minute and a half. If you guys want more time, please let us know. We can wait for a little bit more. Let us know in the chats, or you can unmute yourself. Something is not clear. Okay, I guess I can end the poll now. So, did both of you answer the question, Poonam and Abhishek?
I'm not sure actually. I was trying to click yes, but
I didn't answer, so I didn't even have an option to answer.
Wait a second, then let me see. Okay, I don't. So yeah, this poll is not showing me. Oh yeah, wait a second. I can see it now.
I did see that 2 people answered yes and 2 people answered no.
Yeah. Never mind, it's okay. So 2 of you answered yes and 2 of you answered no, and the others I think are still figuring it out. But does someone want to say why they answered what they answered or what they are thinking? I mean, having this session to be interactive will be very nice. All right, so I guess we'll proceed. It's fine if you have not been able to figure it out, but let's try to think about it in the way we were suggesting, okay, using our meta principles, etc. So the meta principle that I want to illustrate here is the one we actually discussed first. That is, if you are stuck at a decision you make, you go back to the time when you made that decision and you try to see what are the alternatives. So let's see. Okay, how do we proceed here? There are just so many choices, right? Like there are so many ways to join these boxes. The wires can go around and do weird things. But the most natural thing is, okay, joining A with A seems fine. Like this seems the most natural thing to do. You start with A and you join A with A in the most natural manner. And then, okay, what do I do? Okay, I want to join B with B. So this appears pretty natural to do as well, right? Although doing this, I already realized that there were a few other ways to join B with B. Like the wire could have gone around C, many things could have happened. But of all these choices, I decided to join B with B. So I should keep that in my mind. But at now, when I have made this decision and I look at this box C, I realize that I'm pretty much cut off. I cannot go outside. So I cannot go outside. Otherwise, it would have been easy. That's not allowed. I cannot cross the wires. This is not allowed. So no matter how I try to get to C, I'm always stuck. I cannot go through the box. That's not allowed. So it seems like I am stuck and this is a difficult problem, right? So suppose you are trying to convince someone, like another way to say, suppose you are trying to convince someone that, look, this is not possible. This task is not possible. How would you convince them, right? Say your friend or, anybody. It could be your partner, your friend, or your teacher. And now you are connected. So how would you go and convince them that this is an impossible task? So let's say I try to convince Poonam that this is an impossible task. So I would tell Poonam that A is connected with A, right? We have to do that. So let's do it in the simplest manner. And I have done this currently. A is connected with A. Already here, Poonam can tell me, oh, there were many ways to connect A with A. You could have gone around. You could have done some weird things. You could have done this. I mean, is it different from the way I have joined it? That is one question, but at least you could have done it. So already you can see that the argument of impossibility is a little iffy, right? We need to worry about these cases, right? It is important to follow this logical thought and this pattern of deduction. If you're already comfortable with it, that's great. But if you're not comfortable with it, then this is something to learn. Now, okay, so let's say that we have somehow made this decision and we now want to show, oh, from this decision, is it possible to complete our task? So B is now to be connected with B, okay? And here we decided to join it in the way we have drawn the wires. B is connected to B, correct? Okay, here Poonam is already saying, no, there were other ways to do it. You could have gone around the box C, but you did not do that. You made this decision. And we are like, yes, we made this decision. We have to worry about that other decision that we have not made. But at this point, we can at least convince Poonam that C is not connected with C, because clearly we have cut off C in a different region. There is no way for the wire to reach that box C. I hope that is visually clear to everybody. Okay, great. So that is not possible. But then let's try to we are stuck, right? Here we are stuck. We cannot make progress. So let's go back to the last decision we made, which is what Poonam would also be pointing out. The last decision we made was to join B with B in this fashion, in this direct fashion. So let's try to think what other ways were there to join B with B. So let forget this dotted wires. I'm trying to erase them. So what other ways are there to join B with B? If somebody wants to suggest something, or unmute themselves and give an idea, that will be great. Okay. We have at least one suggestion. I tried the deformation technique, but it is not work. So the question
Yes.
I want to tell everyone now is that we are trying to find an alternative to the choice that we made of joining B with B. And that choice is really the heart of the puzzle. Sorry, one second. My pencil seems to be misbehaving. Yeah. So the choice is to go from B to B, but wrap around C. This is the other choice that we had not explored. Is the task still impossible? Well, suddenly we realize, oh wait, this is not impossible. This is easy. So the takeaway here is not so much that, oh, this puzzle can be solved. Yeah, it's a fun puzzle. Give it to your parents, your friends, your enemies, depending on whatever outlook you have. But the thing to take away here is that you can solve it without requiring some stroke of genius that is somehow unfortunately displayed in a lot of math videos. Yes, there are math geniuses, but what they do and what qualifies them as genius is not what is shown in these YouTube videos. Here, we can be much more modest about what we are doing and still make good progress on a problem. All we did is think logically. We made some choices, we got stuck, we went back, we undid those choices, we made a different choice, and we succeeded. Seems simple enough, right? And sometimes it is indeed this simple. Sometimes it is not. Of course, that's where the fun is. If everything were too simple, then it would not be so fun. But if something is not clear about this whole exercise or about the principle, please write in the chat or unmute yourself and ask. So Rintu, you had written something about the deformation technique. If you want to say about how that relates, like what were you trying or how it relates to the solution currently, please feel free to do so. If you haven't understood something, you can ask us. Yeah, it's good that you try something new, and maybe even your technique gets a solution. You should think about it deeply after the video, right? So I'll wait for probably a few seconds or something like 10-15 seconds and see if people have digested this or they are still unsure about what's happened. Before we move on, here's your chance to let us know how we are doing. You can write your opinion in the chat, or you can unmute yourself and tell us how it's been going for you so far.
I think they are choosing the sixth option.
Yeah. That's what we should have written, a sixth option, that you can stay mum also.
One guy is feeling.
At least one guy has said excellent.
No, now two.
Good. So Ishan is good.
Rintu is excellent. Kushagra is excellent.
Okay, great. I think.
Yeah, that's nice.
All right. Yeah, that's one more excellent than I had expected. So it's so let's move on and let's see what our next puzzle has to bring. Oh yeah, I think PowerPoint gets stuck. Okay, good. So this is a famous puzzle. Maybe some of you might have encountered it. At some point, it was very popular for the finance companies to ask this question. This question has a bunch of rules, so bear with me as I explain them. But it should become clear. And I also feel like if you put your mind to it, you can solve this question. But of course, it is a tough question, all said and done. So, okay, we have 4 people, as you can see in the diagram. We have 4 people who are on one end of a bridge, and they have a torch. So yeah, I apologize for this not so clear torch, but there is this torch over here, which is sending out some black rays, which is supposedly light. So you have 4 people who are trying to cross a bridge and catch a train. Okay, the train is running away. If you are from Bombay, you would have certainly done this. I have done this many, many times with not 4, but 4 million people. Now, we have these people, you can call them ABCD in any order you like, just to be sort of more concrete about it. We can call this, I guess, yeah, what the hell, let's just go for this. So this is A, B, C, and D.
I think you should label it in reverse order because the time that a child would take, it's better to do that.
But so let's give this, let's give the girl the faster time. So this is A, this is B, this is C, and this is D. Okay. So yeah, pardon my handwriting. I can try it. Yeah. Oops. Sorry. You guys can keep reading the rules of the game until I learn how to write D. Okay, good. So they need to cross this bridge and catch the train, and they take a lot of time to do it. Okay. So some of them can do it faster and some of them require more time. So A is the fastest, she can cross it in 5 minutes. Then B is taking 7 minutes. C and D are very slow. They take 20 and 25 minutes. The bridge can only accommodate 2 people at a time. The bridge is not a strong bridge. So the moment the third person steps on the bridge, it cannot take the weight. It will collapse. So only 2 people can cross it at one time. And they need a torch to cross it because it is dark. So they cannot walk. So yeah, you might think that, oh, if somebody crosses the bridge, can they not shine a light to the other side? No, they can't. It's a long and dark bridge. So when in the beginning, if you say, oh, let's say these 2 people walk on the bridge and go across, now the torch is on the other end. Now, so if A and B, suppose you decide that let me get A and B to cross the bridge, then A and B reach here. So this is A and B reach here, but the torch is also here. So now C and D cannot cross the bridge. One of A and B has to go back to get the torch on the other side. It is fine for just one person to walk on the bridge. It's not a rule that 2 people need to walk. It's only that not more than 2 can walk. Okay? And the question here is that the train is about to depart in 45 minutes. Can you devise a strategy? Can the people devise a strategy in which they can catch, all 4 can catch the train? That is the question. Can all 4 people catch the train while respecting the rules that we have laid out? And yeah, I mean, if something is not clear, please ask. This is a tough question. I think we'll give you some time to think and ponder over it. Something might not even be clear. You might feel, I mean, people can come up with very inventive ways to solve it, which are lateral thinking. We would love to hear those ways, nothing against them, but this is a sort of a more mathematically oriented question. So try to stick to the constraints of the group. At some point, you'll see a poll pop up on your screen, but take your time. I remember struggling with this question for a fair bit. I was like, I don't know how many years ago, probably some of you were not born then, but yeah. I remember the location. I just don't remember the time. It was at the stairs of my maternal grandmother's house, and I found this puzzle from some random source.
How many trains did you miss while solving such puzzles?
Yeah,
There's a question.
I wanted to miss the train actually. So okay.
So if we are walking together on the bridge, D will be left far behind than A. So how is it supposed to be? Is it mandatory for A to walk with the same speed as D?
Okay, so that's a good clarification by Ishan. Yes, because D can't walk too fast. Since D can't walk fast, A and D have to walk at the slowest speed. A can always walk slower. Because if A walks at a faster speed, she'll carry the torch away and then D can't walk. So you are right. If 2 people are crossing the bridge, they have to obey the speed limit of the slowest person.
So would you like to start a poll?
Yeah, I'm doing that. The poll should be there on your screen, but yeah. Does anybody want to share their thoughts via the chat or via the Q&A or speak up? Any suggestions about how we might approach this question? Okay, never mind. Let's try to solve it step by step. Okay, so again, we will demonstrate here the meta principle that we have been talking about, which is that is if you are stuck, you go back to the last decision. So let me just get my pen together. Yeah. All right. So I of course can't keep drawing that huge picture again and again. So we are just going to imagine that this is the bridge, and to the starting configuration we have is that the left of it we have 4 people, A, B, C, and D, right? And to the right we have the train. So the train is here. Okay. And just so that it is convenient for you guys, let me write down what is the time required. So A requires 5, B requires 7, C requires 20, and D requires 25 minutes. Okay, that is what the constraints are. So, and so the torch to, I don't know how I'll draw the torch, but let me just use this asterisk to denote the torch. So initially the torch is, so this is our torch. This is the torch. So initially the torch is with the 4 people and they need to cross and go to this side. Okay, great. So what should be your first step? There are just so many possibilities, right? You can choose any 2 and send them across. And to top it all off, you can send just 1 person across. But obviously that is stupid, because if you send any of them across, the torch goes with them and they have to come back, because what will the other 3 do? Right? So at least those we can kill. Now you can send any 2 across. Now which 2 to send? Not clear. It seems like sending the people who walk the quickest might be a good idea, because at least we are making some progress. We are spending some time. We have a budget of 45 minutes. So train leaves in 45. We have a budget of 45 minutes and we have to send all 4 of them across. So, okay, let's try to at least get as many across as possible. Seems a natural thing to try. Let's try that and let's see what happens, right? So if we follow that, well, what would we want to do? We would want to select A and B in the beginning to cross the bridge, right? Just 1 second. I'm trying to get the Zoom window to behave well. Yeah. So we would like A and B to cross the bridge in the beginning. So A and B cross the bridge. Yeah, Abhishek?
No, there was a fly bugging me. Don't
So
bother.
A and B will cross the bridge. What will be the scenario then if A and B cross the bridge? Well, AB will be there. You would have wasted 7 minutes, because B is the slower guy. So you would have wasted 7 minutes and the torch would be here. So, okay, A, B, torch. Here are C and D. And okay, you have wasted 7 minutes in your time. So here the time was 0. Here you're 7 minutes further into from the start of the question. Now what should we do? Well, C and D are both stuck there. They can't do anything. So we have to send one of A or B back. Sending both of them back is pretty pointless, because you just return to the starting state. So, okay, it seems natural to send the quickest guy back. So we will send A with the torch back here. Okay, let's do that. If we do that, where do we end up? Well, we end up with a situation where we have A, C, D. We have the torch here. And we have B on the other side. And we have incremented our time count by another 5 minutes, right, in doing that. Right, so A went. So A this time crosses the. Last time AB crossed it. This time A crosses it. Okay. So now we have to go 1 step further. So we have to send some 2 again on the other side, right? So again, it seems natural to try and send A and C, because they are the quickest amongst the 3 that are here. So let's send A and C to the other side. So A and C now will cross the bridge. So if A and C cross the bridge, we reach this configuration where we have D, we have A, C, and B, and the torch is here. And we have another 20 minutes that are added to our counter, right? This is what has happened.
So let's explain why 20. Let's maybe just do.
Oh, good. So when A and C walk together, as Ishan also asked, when A and C walk together, they have to walk at the speed of C, because if A tries to walk too fast, the torch has to go with A. Then C is basically left in the dark. They can't walk. So that's why, that's as given in the question, both of them need the torch to cross the bridge. Yeah, we could have specified this a little better, but these are the constraints of the question. Okay. Great. So I hope everybody is following the flow of thought up till now. If something is not clear, you've lost me, then let me know what's not clear. So let me reiterate what we have done. We have decided to send the quick guys who walk quickly first and hope that we are able to make it in 45 minutes. So in the beginning, in the first step, we send A and B across. It hits us by 7 minutes. Then we send A back because the torch is on the other side. That hits us by 5 minutes. Then we send A and C across, which hits us by 20 minutes. And we are in a situation now where the torch is on the side of the train, A, C, B are on the side of the train, but D is left. And if you look at the time we have used up, 32 minutes. That gives you only 13 minutes to get D to this side, right? Because 32 minutes are gone. In this commotion, a total of 32 minutes is already done. So you have only 13 minutes remaining. And this is impossible, right? Because D alone takes 25 minutes to walk. It doesn't, the torch is not even there, but forget that. Right now, there is a bigger headache we have, that D alone will take 25 minutes to walk. How is it possible to reach the damn thing in 45 minutes, right? And it almost feels like, wow, this is a very, very difficult thing to achieve, if at all it is possible. But one thing you guys might have noticed is that 45, the budget that we have, right, is 45, which is exactly 20 plus 25, which is the time required by C and the time required by D, right? So in some sense, we want to say that, oh, look, C is going to take 20 minutes and D is going to take 25 minutes, right? That's the constraint. And that itself is 45 minutes. How the hell are we going to get A and B also on the other side within 45 minutes? This almost looks impossible. Can someone tell me what was wrong or what conclusion we made which we should be more careful about in this argument that I just gave about it being almost impossible to achieve the task? So we have 45 minutes for the train to depart. C is going to take 20 minutes. D is going to take 25 minutes. That already exhausts the 45 minutes. How are A and B supposed to also get across to the other side? Or does this mean that this is impossible? Is this argument suggesting that, oh, you cannot do this? And we are stuck, by the way. Here. We are stuck. In this configuration, we are stuck. We cannot complete our task from.
So Ishan has a suggestion. C and D should work together.
Exactly. Very good. So the fallacy of the argument, as Ishan points out, is that C and D have to walk together to achieve the task, right? Because if C and D walk together, then you don't get to do this. You don't have to waste 20 minutes on C and 25 minutes on D. It's just C and D total will take 25 minutes to walk. That is the crux. So the crux here is that C and D should walk together. Okay, good. Now, you can also say that, well, how does it relate to the meta principle? Well, let's see. So we got stuck here last time because we made a decision which led us to a state from where it was clearly impossible to solve our problem. That state is sort of in front of you, where D is left on one side and ACB are on the other side with the torch. So let's go back to the last decision we just made, which sort of ruined the question for us. Also, we have an insight now that C and D should walk together. We have this insight. So let's try to see what happens if we use this insight. So instead of A and C walking together, now we know that the correct thing is to get C and D to walk together, right? Let's make a different choice. Last time the choice was A and C walking together. Now we will get C and D to walk together. If C and D walk together, what happens to our scenario now? So now we get A on this side, C and D on this side, B on this side with the torch. And how many more minutes have we spent? 25 more minutes. We've spent 25 more minutes, right? Because D walks at the slowest pace. So it takes, so we have spent 37 minutes on the task already.
So there is a response by Rintu and Ishan has the same reservation that COD must come back to give the torch, and then how is this going to work?
So from this point, like the point that we just said here, in this state, so the question is that the state we are in currently, from there, are we stuck or can we solve the problem? So I guess, oops, sorry. There is the chat. Let me read the chat. Yeah, that's the problem which further arises. Okay. So are you, so here's a question for you guys to think from this state that I've drawn at the end, right? Is it the case that we can complete the problem or not? If we can't, then we will have to think further. If we can, then that's good. I hope I haven't made any calculation. So I don't see any responses, but yeah. So it did, like, it is quite possible that the problem is not, like, the task is not possible. That is a fine solution, and that could also happen, but you have to give at least some convincing reason. You don't need a proof. So from this point onwards, at least it should be clear whether it is possible or not. So from here, of course, so from here you can see that if you want to give the torch back to A, you would need to send B back, right? Because that seems to be the most reasonable thing to do. Oops, sorry. So from here, the most reasonable thing to do is to send B back, right? Because the B is the quickest. If you do that, that's going to add another 7 minutes. And then, well, where are we? We are at 44 minutes. So we don't have enough time to get A and B across. Okay, fine. So does this mean that now there is no way for A and B, A, B, C, D to actually cross the bridge in 45 minutes, less than 45 minutes? Because we have also exhausted this one attempt we had of getting C and D to walk together. Does anybody have any? So I don't see any responses, but yeah. So it did, like, it is quite possible that the problem is not, like, the task is not possible. That is a fine solution, and that could also happen, but you have to give at least some convincing reason. You don't need a proof. So from this point onwards, at least it should be clear whether it is possible or not. So from here, of course, so from here you can see that if you want to give the torch back to A, you would need to send B back, right? Because that seems to be the most reasonable thing to do. Oops, sorry. So from here, the most reasonable thing to do is to send B back, right? Because the B is the quickest. If you do that, that's going to add another 7 minutes. And then, well, where are we? We are at 44 minutes. So we don't have enough time to get A and B across. Okay, fine. So does this mean that now there is no way for A and B, A, B, C, D to actually cross the bridge in 45 minutes, less than 45 minutes? Because we have also exhausted this one attempt we had of getting C and D to walk together. Does anybody have any thoughts? Yeah, just think about it for like 30 seconds or so, and then we will discuss. Don't presuppose that it must be possible to solve it. If you have a strong argument that you cannot, then that's also something you should just.
So Rintu is suggesting if ACD can go together, meaning three of them can go together, then it would be done, but then that destroys the constraints of the problem. So that's not possible.
Yeah, so that would have worked, but that does not satisfy the constraints. So let me, okay, so fine, I think we can discuss a little more. So let me tell you that this task is impossible. You cannot do it. But how would we go about arguing? So the point is that last time we had an impossible looking task and we were able to do it. This time also, for some time, we thought it's an impossible looking task. And at some point, we felt we can do it. But we gained some insights from it, but turns out that the task is still impossible. But now, can you give a convincing argument as to why? Yeah, of course, you can say that, oh, I tried all the cases. Like I just enumerated all the cases, it's not working out. Which is fine because this is a finite problem. But we can give a reasonable argument here. That is that we know that C and D have to walk together. Otherwise, it's just impossible on the face of it, because C and D walking differently would already exhaust 45 minutes. Now, and of course, like you cannot only have C and D walk once and all the 4 people are reach the other end, because the torch has to come back once. So one person has to cross the bridge at least thrice, right? If it is not clear to you, that's fine. But at least you agree that C and D must walk together. If C and D don't walk together, there is no way for this task to be achieved. So if C and D walk together, we know 25 minutes are gone there. Right? We cannot have C and D walk together in the beginning. If they walk together in the beginning, then one of them has to walk back to give the torch, which is game over there. So C and D have to walk together and then not come back. Right? That is, once they have crossed the bridge, that's it. Which means that initially, one of A and B must be coming back to pass the torch. So therefore, necessarily it must be the case that A and B, you start with A and B. It must necessarily be the case that you start with A and B, you send them across, which is this configuration. You send either A or B across. That is not very relevant to our argument, as you will see. You send either A and B across, you get C and D to the other side. That is the only way to solve the question. And then the torch is on the other side, so you have to send B, in this case B, to the side, to the initial side, so that they can cross the bridge for one final time together with A. But this strategy takes too much time, and we have also shown that there is no other way to solve the problem. C and D have to walk together, and that can only happen once. They cannot walk back. So that this is the only way to arrange that, but even that strategy fails. Hence, this task is impossible.
But perhaps we should mention what is the minimum time they would all take to go across.
So this is the next. So great. So we need you to fill another poll. This time, you need to tell us what is the minimum time. Okay, so let's end the poll now. So one person answer. I don't know. Again, I can't quite see the details. Okay, doesn't matter. So does somebody want to speak up what the minimum time is?
Or write it on the chat.
Or write it on the chat. Actually, somehow the polls are not working well for us beyond just showing us the statistics. Do either of you? Oh, we have 3 people remaining. Sorry. Do any 3 of you want to guess what is the minimum time? It's not too difficult actually, because we have already followed most of the strategy. It is just whatever time was required to complete the strategy, right? Of course, showing now why is that the minimum time, that will again require an argument, but at least we have a plausible answer. So what is that answer? So I think I got a reply in the chat, 51. So let's see. Is it 51? Anybody else? Yeah, let's see what happens if we complete this strategy. So we have already burned how much time? We burned 37 minutes, and it would take 7 more minutes for B to cross. So that's 44 minutes. And then it would take 7 more minutes for A and B to cross to the other side. So that would exactly total to 51 minutes. And we leave this as a challenge to you to actually give a rigorous, in quotes, like at least give a convincing argument as to why this is the minimum time. it will follow a similar strategy as we did. And or you can enumerate the cases systematically. Either way, you will be able to show that this is as good as it gets. Okay. So at this point,
there's a lateral thinking solution there. The D can keep A in his back, and I mean people can carry each other on their backs and whatnot. So those kinds of solutions.
Yeah. Probably in the real world you might use such solutions, although you shouldn't carry someone on your back this way and this. But yeah, here the problem is that the weight would be too much and the bridge would collapse. Okay. So I know the last problem was pretty difficult. There were a few things going on, but I hope you guys understood how things work in Olympiad maths or in this course. Ishan is saying that the speed would decrease. So how are you guys feeling? Now I'm pretty sure some of you would rate, would use one of the lower ratings, but that's fine.
Excellent.
You have one, okay, at least Rintu is feeling nice. Yeah, we just wanted to know the mood so that we can calibrate accordingly. We have just a brief topic to cover and then we'll be done. Okay, I guess the others are not yet writing. Never mind. So I think Ishan is at least following because he did say 51 and Kushagra gave us a lateral thinking solution. So overall, okay, people are still with us. They are not going anywhere. All right. It's time for the next module and this will be much quicker than what we did. But it is to bring you closer to Olympiad maths. Like we are sort of transitioning from the flavor of the how to solve it program towards Olympiad mathematics. And this is a topic which is at the core of any math Olympiad, or at least math Olympiads which are descendants of the International Mathematics Olympiad in the Indian situation. So here's the pigeonhole principle. Many of you are aware of it. I guess we have only 3 people, so some of you might be aware of it. But nonetheless, this is a principle which is so obvious that most of the times we don't ask for a proof of such a thing. But its uses are remarkable. And by which I mean that even in cutting edge combinatorial research, the ability to apply this principle innovatively is paramount. So what is this statement? I am giving you an instance here just because I use these numbers just because the picture that I found here was too cute to not use. So if there are 10 pigeons and 9 pigeonholes, now what are pigeonholes? Apparently these were things that people in the older days were using. We don't quite understand what they are, but pigeonholes also means some kind of sort of shelved columns in which you usually keep mails in an office or something. But yeah, you guys might have not seen it. But nonetheless, just imagine them as boxes, as like slots into which pigeons can be fit. So you have 10 pigeons and 9 pigeonholes. And if 10 pigeons occupy 9 pigeonholes, then one pigeonhole must have 2 or more pigeons. Right? You can see that if these are 9 pigeonholes and the 9 pigeons have all been occupied, 9 pigeonholes have all been occupied, then the 10th pigeon doesn't find a place to go. Wherever this pigeon decides to go, that pigeonhole is going to have 2 or more pigeons. Right? Pretty obvious. And if you generalize this principle, it becomes the pigeonhole principle. Just a moment. I'll just wet my vessel. So here it is. If there are n plus 1 pigeons, so n is just 9 in the above example. So this is nothing to be afraid of. So if there are n plus 1 pigeons and n pigeonholes, then one pigeonhole must have 2 or more pigeons. Yeah, Abhishek.
So there's a question. Ishan says, if some pigeonhole has more than 2 pigeons, then some must be empty.
Absolutely. If some pigeonhole has more than 2 pigeons, then some must be empty, but that is not the pigeonhole principle. That what you are suggesting is correct. I think, Abhishek, do you have more to add?
No, sorry. You go ahead.
Yeah. So you are right, Ishan, that if it so happens that one pigeonhole has 3 pigeons, then you have 7 remaining pigeons and 8 pigeonholes. So one pigeonhole will be vacant. which is what you are saying. But that is not the pigeonhole principle. The pigeonhole principle is trying to find you a pigeonhole with many pigeons. Of course, in a question, you might use anything, and the principle you are saying might be useful as well. But the pigeonhole principle, as stated, is what we are saying. But thanks. Yeah, that what you are saying is that. Yeah,
I would like to add one thing, like
yeah.
You can just imagine a situation where every pigeon is in a single hole, pigeonhole. So this is also possible. So yeah, so underlying thing is you are trying to make sure that there is one pigeonhole which has more than 2 or equal to 2 pigeons. That's all. You are not doing anything else.
Yeah, so Ishan, you are right. Ishan, you also suggested this is a corollary of it. I don't think so, because yeah, I mean these things are kind of
Both statements are true. Both statements are true. So now,
yeah, that's what I didn't want to get into the logical connectives here, because yeah, there are hilarious stories about those. Maybe we can discuss them another time. But okay, we understand the pigeonhole principle. We also understand Ishan's principle, so we can use either. Okay. So let's move on. Now here's a toy puzzle for you, which is just an application of the pigeonhole principle. This is not really something I'm going to give you time to think about. I'm going to solve it on the spot, and then I'm going to give you a puzzle based on this. Okay. So Madhav invites 5 of his friends to his home, and some of his friends shake hands with him. So handshake is mutual. Of course, if I shake hands with someone, then well, they have also shook hands with me. Here's the question. You have to show one of the following is true. Now, yeah, here you can actually do an exclusive or, but okay, never mind. Show that one of the following is true. There exist 3 of his friends. That is, there are 3 friends that he has invited who have shook hands with Madhav. Yeah, him here is Madhav. So this is Madhav, right? And same thing, this is Madhav.
So Rintu is restating the pigeonhole principle in the functional language. He's saying if number of holes is less than number of pigeons, then there is no one-to-one map from the pigeons to the holes.
Yes, that is also another way to say the pigeonhole principle. Yeah, and there is also a generalized pigeonhole principle. There are variants of the pigeonhole principle, I think, but they are all based on the same philosophy that if you try to pack in too many things into few spaces, slots, boxes, one box will be overcrowded. Yeah, the innovation is not in thinking about which principle is going to get applied. I think the innovation lies in thinking about what the boxes and the pigeons are. So don't worry too much about how you state the pigeonhole principle, because more important than that is to realize that, oh, the pigeonhole principle is applicable here, because the questions don't usually follow a template. Like it shows up at unexpected places. That's all I can say. Okay. So in this situation, let's try to attack the question at hand. We want to show that there are 3 friends in the party who have either all shaken hands with Madhav, or all 3 of them have not shaken hands with. So please pay attention to the language of the question, and if it's not clear to you, let us know. Now, how do you show this? This might be very easy for you guys, or because you've seen pigeonhole principles before, but nonetheless, let's just go through with the argument. So let's suppose that we have Madhav here. I'm just going to draw a dot to represent Madhav. Okay, he is our person 0. Or friend 0. Friend 0 is really just Madhav himself. Just don't worry about the 0 part of it. So we have 5 friends here, and I'm going to just call them F1, F2, F3, because I don't want to give them names, especially now with parents naming their children. Clearly, this could very well be the name of some person. And F5, yeah, Brock Lesnar fans out there. And what do we want to know? So these are the 6 people who are there at the party. We want to know the status of each person with regards to whether they shook hands with Madhav or not. Now, there is a very illuminating visual way to represent this situation, which is just the following: that if they have shaken hands with Madhav, you just draw a blue edge. Okay, if friend 1 shook hands with Madhav, you draw a blue edge. If they did not shake hands with Madhav, you draw a green edge. Okay, simple. And similarly, you will have edges to these 3 other remaining friends, F3, F4, F5, which we are not showing right now. But you can clearly see it's almost clear just by inspection that no matter how these edges line up, 3 of them will always be colored the same, right? We will obviously prove this, but in any situation, like let's suppose the situation is here, the one I am showing. In this situation, what has happened? F1 has had a handshake with Madhav, F2 hasn't, F3 has, F4 hasn't, and F5 has. In this situation, F1, F3, and F5 satisfy our hypothesis because there are 3 people, F1, F3, and F5, and they have shook hands with Madhav. And how do we prove this? That there will always be 3? Okay, so here is where this idea of thinking about the penultimate step, that principle that we said, really helps. Okay, this is a very simple question, I understand that. But we are trying to illustrate a general principle, and of course, this is a trial class, so the real meat will be in the actual classes. So let's see. You want to define pigeons and pigeonholes. Okay, that is usually the point. So I think Olympiad questions might as well write use pigeonhole principle because that gives no hint at all. The real difficulty is in identifying what the holes are and what the pigeons are. Now, what should be the holes for us? So, okay, forget the fact that I'm writing in green. Yeah. So what should be the holes for us? Well, in the end, what is your conclusion? That there are many pigeons in a single hole. So you want to find 3 friends with the same property, right? That is what the question reads, like find 3 friends which have the same property. So just by the syntax of what this statement is, let me write it down. Let me use a different color. Okay, good. So 3 friends with some property. So, okay, with some property. And look at how pigeonhole principle reads. 2 or more pigeons. I mean, forget the 2 or more. Forget that number. Okay, 2 or more pigeons in a hole. Just by syntax matching, you should be able to see that the friends should become pigeons and the property that you are hunting for should be used to define the holes. So in this case, the holes will just be the following. So there are, sorry, was there a comment or something?
No, I don't see any comment.
So what will be the holes? The holes will be very simple. So the holes will simply be, so the pigeons, it's probably easier to first define what the pigeons are. Pigeons will be friends, will be these guys, F1 up to F5. And what will be the holes? Whether they had a handshake or they did not have a handshake. So did they handshake? Or let me not write it this way. Let me write it as yes or no. So this is yes or no to whether they shook hands with Madhav or whether they did not shake hands with Madhav. So here you have 5 pigeons. Sorry, you have 5 pigeons and 2 holes. See, you have 5 pigeons and 2 holes. So let me again just emphasize one thing, that this is what are the holes? The holes are like whether there was a handshake or not. Depending on that, we will place each friend in the corresponding hole. If they shook hands, we'll place them in the yes hole. If they did not, we'll place them in the no hole. So there are 5 pigeons, 5 friends, and 2 holes. The pigeonhole principle we stated in the last slide did not cover this case per se, but I guess all of you can see this, that one hole will have 3 pigeons, right?
At least 3. Let's say at least 3, otherwise there may be confusion.
Yeah, we'll have at least 3 pigeons. Yeah. Greater than equal to 3 pigeons. And let's say that it is the yes hole, because it doesn't matter. If it's the no holes, we will choose out these people. So the pigeons, like in this diagram that I have drawn, they happen to be F1, F3, and F5. And whatever pigeons you find in that hole will satisfy the hypothesis, because all of them either have shaken hands with Madhav or they did not, or they have not shaken hands with Madhav. So this is how a pigeonhole argument is carried out. If something is not clear, then please let us know. If it is clear, then great. I'll wait for a little bit to let you guys ask questions if you have.
Maybe you can state the general version that you're using here, just to be very clear.
Yeah. That would be good. So, what is the general principle, general pigeonhole principle that we used here? Yeah, let me state it on the next slide. But this, so the thing that we used here, I think this is what Abhishek is saying. This thing that we used here, where my laser pointer is, that was not exactly n+1 pigeons in n holes, but it is kind of similar in spirit and is certainly not more difficult than the one that we just saw using the 9 and 10 pigeons example. 9 holes in 10 pigeons example. If you have 5 pigeons and 2 holes, then one hole will have more than 3 pigeons, because if there are only 2 pigeons in each hole, where will the 5th pigeon go? Right? It's the same idea. So if there are no questions, let me move on. What did we learn from the last slide? And I'll also state the general pigeonhole principle. We learned that it is often useful to capture the problem in a convenient visual way. It helps us think like in the last example, we had 5 friends and Madhav, and we denoted them by 6 vertices or dots, and we drew lines or edges between them to denote whether a handshake had happened or not. Right? That really helped us think about the question, argue about the question, and this is the beginning of graph theory, some might say. We have not really defined formally what these things are, but we don't need. Right? And thinking about the penultimate step is very useful. Like in this example, okay, it was simple enough that you could have arrived at it just by visual inspection. But in a question about pigeonhole principle, which is way more complicated, you have to keep asking yourself, okay, what could be a possible definition for hole? What could be a possible definition for my pigeons? And if you can just think about what definitions could lead you to the question, could lead you to the solution of the question, could lead you to the hypothesis you're trying to prove, it often reveals itself that, oh, this should be the definition. But now, oh, I see two questions in the chat. Okay. So let me write the general pigeonhole principle. I apologize somehow. Yeah, I did not mention it on the slide. I should have, but this is the general. And now you'll have to bear with my handwriting. Okay, let me tell you one more thing. It is not true that as you grow mathematically, your handwriting deteriorates. That is something that had happened to me well before I started mathematics. So
no, I think that cannot deteriorate. In your case, it couldn't have.
It couldn't have deteriorated. You see, there are some advantages of having a bad handwriting. You can always say why you got low marks. Your handwriting will pass. So general pigeonhole principle. So if we have n pigeons and m and k holes, probably k is better.
Yeah, k is better. M and it sounds very similar.
K holes. Can someone guess what should be the thing? Then one hole has at least how many pigeons? So has at least, one second. There is some number I want to fill here. Pigeons. What should be that number?
Since people are thinking that, I just want to add one thing.
Mm-hmm.
In these questions, usually, we don't have this information that this question will use pigeonhole principle. So we need to, when we are thinking about the solution, then maybe we will come up with this situation where there are things and we need to show that, okay, there are that many, at least these many things should be satisfying some property. So, yeah, so you will not have this disclaimer that this problem is going to use pigeonhole principle. That is our, I think, main thing to say. This can come up in any random puzzle, in any random question that you might end up using Pigeonhole.
Okay, so we have one answer. N question mark K. I suppose he means
Divide by.
divide. So that is correct. It's just to be more precise, it is N over K, the ceiling
Ceiling.
function of that. What does that mean? It just means that, look, if N over K is not an integer, if N over K turns out to be 3.14, so we don't want to say that there are pi many pigeons, at least pi many pigeons. We can say that there are at least 4 pigeons, right? Because there is no way to, if you are saying there are at least 3.14 pigeons, well, you also know that the number of pigeons is an whole number. Then the only possibility is that there are at least 4 pigeons, right? So that's why you put a ceiling, which means that the answer is 4. That's all that is going on. Otherwise, you were spot on. I think it's also because you cannot write ceiling in here, so maybe you actually meant ceiling. But if the general pigeonhole is not clear, please do ask. I think it should be clear. So let's move on. And this is not the toy puzzle. This is the boy puzzle. So it's the same setup. You have Madhav with 5 of his friends doing a party or playing video games, Xbox, whatever. And here you have to show something different. And please note the difference from the last question. Okay. This is actually a very famous puzzle or a very famous problem that is taken in almost every Olympiad preparation, quant interview preparation, or the start of graph theory, Ramsey theory. This, you cannot avoid this problem in your mathematical career. This will come up. So you have to show one of the following things is true, that there are 3 people at the party. So now Madhav is not provided any special status. Earlier, we were always thinking of Madhav, like, yeah. Here, there is no special status. Nobody is afforded any special privilege. It's a secular country. But you have 3 people, and you want to find, these 3 people should be such that all 3 of them have shook hands with each other. Or there are 3 people such that all 3 of them have not shaken hands with each other. So
here the problem is not stated clearly, because see, in this problem, it's not just that the friends shake hands with Madhav, it's that...
Oh, sorry. Thanks for friends shake hand with... Thank you. Yeah, I forgot to change that. Each other. So yeah.
Some people may shake hands with each other, some may not. It's their decision. They are completely free to choose who they want to shake hand with. But yeah, handshakes are always mutual. If one shakes hand with the other shakes hand with one. So that is the situation. And then the question is to show that you can always find 3 of the people who are attending the party with the property that all 3 of them shook hands with each other, or all 3 of them did not shake hands with each other. Meaning mutually they did not shake hands with each other.
Yes, that is right. Yeah, I apologize for that mistake. So we already made 2 and 2. Luckily, this is the last puzzle. I cannot do the third mistake now. So, oh, wait a second. Here's the third one. So here in our visual language, what are we asking you to find? So Madhav was F0. We never used it. So F1 to F5 return. Now any 2 friends can shake hands. And we want you to find 3 friends. So say we don't know how this pattern of edges looks like. Like some could be green, some could be blue, right? Green denoted that they did not shake hands. Blue denotes that they shook hands. What we want to find are 3 friends. So let's say that maybe the answer is F1, F4, and F5, right? Then we want these 3 friends to be such that the edges, oh, sorry, I have to convert it to the edges between these 3, the 3 possible edges, 3 possible lines, or the status of the handshakes should all have the same color. That is, the friends F1, F4, and F5, none of them shook hands with each other. If one of these edges were blue, that is not good. That doesn't satisfy the hypothesis. That doesn't satisfy what the question is asking. Because here, F1, F4, and F5 cannot be the 3 people the question is asking. F1 and F4 have had a handshake, but F4 and F5 haven't. That's not good. So in graph theoretic terminology, which you don't need to know, I'm just saying it, is that it is a monochromatic triangle. That is what you are hunting for. A triangle in which all the edges have the same color. So yeah, that's what we need to do. And actually, the argument is not going to be too different from the one we already did. So to help you guys get started, I'm going to do a bit of it, repeat what we did in the past question, and then I'm going to leave it to you to finish the argument. So from
But
the
can we ask if they understand? So it's
good.
the problem may not be clear.
So if the problem is not clear to you, please let us know. Just shout out that please can you explain it again or something like that, and or just write it on the chat. I think it is there are two ways, either nothing is clear or everything is clear. It's generally dangerous.
Okay, let's assume that things are clear. What else?
Go ahead,
Okay,
because
we have to hope for the
time.
best, prepare for the worst. But so from the past, the argument we had just done, right? We know that there are three friends of Madhav. So this is our previous question. There are three friends, or let me write three. There are three friends of Madhav, which is F0 in our case, which have all had handshakes with Madhav. I don't know if handshakes is a noun, but okay, I'm committed at this point. Which
or three which do not. So
or three which do not. Yeah, we could have also had the other possibility, but we are assuming that right now we are in the situation where we had, or they did not. Right. So this is what. So there is a chat question.
I don't see any question.
There is a chat. Let me see.
It is clear to me. He says the question is clear.
Okay, good. So we already know that there are these three people who are all making the same colored edge with F0. Let's just assume that the edge has colored blue. Okay. So F1, and let's also assume those three people are F1, F2, F3, because why does it matter? Naming cannot matter, right? It could, you just assume it's F1, F2, F3. Now, can you complete the argument from this point onwards? Can you figure out those three people? Can you prove that there will always be three people, which will satisfy the hypothesis of the question? That is, either all three of them would have had handshakes, or all three would have not shaken hands. And actually, you can find these three people amongst the four people which are F0, F1, F2, and F3. You don't even need to consider F4 and F5, given that I have already told you that F0 has had handshakes with F1, F2, and F3. So yeah, I'll pause for about a minute. It's not very difficult. Just try to think of the cases, and it should be apparent that this is true. If you want to speak up, this is your last chance, because well, okay, I want to say this is the last puzzle we have, but that would be lying. So, but yeah, it would be a good time to speak up if you want. So anybody has any thoughts, like, please write it in the chat. I'll just redraw this a little bit better, and then I will check.
So Kushagra says answer is A. There exist three people who shake hands with each other.
So Kushagra, here we don't have to choose between A and B. The question is saying that you have to show either A is true or B is true. If I speak in Hindi, वो कह रहा क्वेश्चन सवाल ये पूछ रहा है कि या तो A सही है या B सही है. आपसे ये नहीं पूछा जा रहा है कौन सा सही है. इसमें थोड़ा सा अंतर है सवाल, जो मतलब आपको चूज नहीं करना है ए सही है या बी सही है, आपको ये साबित करना है कि इन दोनों में से एक तो जरूर होगा.
ओके सर.
All right, so let's finish the argument from here. I hope you guys would have figured out or are very close to figuring it out. So the point is that here's a simple thought, like can any of the edges that are going to be between F1, F2 and F3, right? That is, if you find any two people among F1, F2, F3 which shake hands with each other, let's say F2, F3, if they shake hands with each other, so I'm just drawing this as a dotted edge for now because there is an if they shake hands with each other, we are done, because look at the
Number 20, page number 20, or I don't know.
Oh yeah, good. So if you look at these three guys, F0, F2 and F3, they are three people, all of whom have had handshakes with each other. So A becomes true, right? But if it is the case that, so what did we just conclude? The first thing is, what did we just conclude? We concluded that if any two people amongst F1, F2 and F3 have had handshakes, then we are already done, right? That means that no matter which two people I pick up, so if I pick up F2 and F3, it means that they must, so how should I do the argument? I should do it this way, that if F2 and F3 are blue, the edge between them is blue, I am done. I have already found A to be true. So let me assume that that is not the case, that F2 and F3 induce a green edge. I will similarly argue for F1, F2. If F1, F2 is a blue edge, I would be done because F0, F1, F2 would be a blue triangle. And to finish the argument, let's consider F1, F3. If F1, F3 is a blue edge, again I am done because F0, F1, F3 is a blue triangle. However, now you see what the problem. The problem is if you make all those edges green, F1, F2 and F3 from a green triangle, right? Which means that either A was true, and if you assume A is not true, then B becomes true. So this is just a simple like logical implication here. So let me write that logical implication down. But before that, I just want to say that we have found F1, F2 and F3 in this case, which form a green triangle. So we were just using this implication, which I think is kind of very natural. People don't know it formally maybe, but it is not too unnatural to say that, to show that A or B is true. Let me write it here. To show that A or B is true. So by A, I mean the statement A. By B, I mean the statement B. And this V that you are seeing is a logical symbol which is used for what in English we call OR. Right? This is just the same as saying that not A, that if A is false, if not A, this implies. So if either A is true, in which case A or B is true, or yeah, I mean, you understand, I won't go into the logical implications right now, but this is not, you don't even need to follow the symbolic thing I've written here. It's just natural to say that if I have to show that statement A or statement B is true, then either statement A is true, or if I assume statement A is false, statement B is true. These things are the same. Like this shows that one of them has to be true. So let me see.
There's something in the chat.
We have two holes. One must have 2 and another must have 3 pigeons. Yes, that is right. That is the. I don't know what Rintu meant by the holes and the pigeons, or for which part of the argument this was.
Maybe he means for the first part of the argument where F0
yeah, this is the logic we used in the previous question, from which we concluded that there are three people which share the same status of handshakes with Madhav.
But still there is a little bit of a problem there, because we are not concluding that one hole must have 2 and the other hole must have 3. All we are concluding is that there is a hole which has at least 3.
Yeah, so that is right. That what the way we stated the generalized pigeonhole principle is that one hole must have at least 3. But I think maybe that's what Rintu meant, that one hole will have at least 3. So if it's not clear, please stop us and we'll be able to.
I think his statement was about this fact, this F1, F2, and everything.
So in the end, we wanted to find a monochromatic triangle within these 4 people. So here the argument is that if any of the friends F1, F2, F3 shake hands with each other, they will form a blue edge. And then along with F0, that blue edge will become a blue triangle. So if that would make A true, A would become true at that point. So if this is not the case, if this did not happen, that means every 2 friends from amongst F1, F2, F3 formed a green edge. That is, they did not shake hands. But then F1, F2, F3 becomes a green triangle. So that completes the argument. Okay.
I think, do you have any pigeonhole kind of argument to say that without using these edges and all? I think that Wintu was trying to do that.
Okay, I see. I am not.
The pigeonholing happened only with the first, where F0 drew 3 edges. That's where the pigeonholing ended. After that, it's basic reasoning.
Okay.
Yes.
So if I wanted to say it again, I would just have said that, okay, assume A is false. Assume that A is false. That you cannot find 3 people who shake hands with each other. Then naturally you are led to the conclusion that every edge between F1, F2, F2, F3 and F1, F3 is green. That's what the argument was.
Yeah.
So, yeah, and I think, I hope people followed, and we can go to the next slide.
So, okay, this is your last chance to let us know, because yeah, we'll be ending the presentation shortly after this. How did you find it?
I think let's leave this for the survey.
Yeah, let's leave this because yeah, we've asked them too many times.
Yeah.
This was not so much of a puzzle as in lecture. Yeah. So let's move on, and the last few things we want to convey are what's going to happen next. So of course, there are many more challenging questions that await you in the full course, which is going to be basically all these puzzles you saw on steroids. The actual program tentatively will start on 3rd Feb, and the details will be sent to you via email. And of course, there will be details about how it will be conducted, the logistics, the payment, etc., payment details, and all of those things will be in the email. And of course, we wouldn't have left you without a puzzle. You knew that. So just, yeah, another important thing, we thought we'll give you an outline of what would happen in the How to Solve It program, which is also the first module of the Olympiad program. We'll cover all these topics that you can see on the screen, and they will be covered in the form of games and puzzles with a flavor of Olympiad mathematics, because these themes also show up in Olympiad mathematics. And the hope there will be to get you to sort of have a streamlined thought process to solve problems, and at least help you to imbibe some of the principles of mathematics or mathematical thinking. Okay, so here's the final question we want to leave you with, and we hope you solve it and send us your solutions. So let's say there are 3 bins. So you can see that there are these 3 bins holding tennis balls in front of the picture. And there are some number of balls in each bin. So we don't know. So this number of balls could be very arbitrary. Like this could have, I don't know what's my 147 balls. This could have probably 111 balls. And this could have 42 balls, something like that. It's arbitrary. And at any step, so this is what you're allowed to do. You can choose any 2 bins of your choice. So let's say you choose these 2 bins. You are allowed to add 1 ball. You have to, rather, after choosing these 2 bins, you have to add 1 ball to each of the 2 bins. So this will become +1 and this will become +1. So you will now have 43 and you will have 112. Right? So it's a very simple procedure. Each time you choose 2 bins, you put 1 ball in each bin and you repeat. You repeat this procedure. So yeah. The question is, so yeah, let me just make sure this is clear. You repeat the procedure. Now, the question is, can you equalize the number of balls in all the 3 bins, irrespective of the starting configuration? So this 147, 111, 42 are just numbers I took arbitrarily. It could be any damn number. And the question is it always possible to equalize the number of balls by following the procedure we outlined? And if you can answer that, we want you to generalize this to any number of bins. So this 3 over here, try to do it for 4, for 5, and then for n, for any n, right? Generalize this. So that is the question. And please send us your solutions or your suggestions, your feedback on this email ID, contact.smartsolver@gmail.com, which is also available in the form you filled or on our website. And that's it. We are at the end of our presentation. It took longer than I thought, but I hope you had fun.
So don't worry about the survey or feedback. We will send you a form, Google
Okay,
form.
yeah. We might even send you a
Yeah,
feedback.
so you just have to fill in some.
If you have
form.
any feedback for us currently, let us know, or else we will call it